Yo, in this video, what we're going to do is we're going to talk a little bit more about vectors, and actually we're going to wrap up the idea of vectors, and we're going to look at some pretty complicated situations with vectors. So pay very close attention here. All right. Now I have to tell you guys about this this idea of unit vectors. It's not really part of the IAB syllabus. You won't get dinged for not using unit vectors, but if you understand them now, it will make things a lot easier for you. And especially when you study vectors in your math class, you will amaze and wow your math teacher for having knowledge of this already. You should act as though you don't know it, though, when the topic comes up to surprise them. Anyway, a unit vector is... these are very cute things. These are little vectors of length 1 unit pointing along the x and y axes, okay? Where I is the unit vector along the x-axis. It's got a really cute little symbol. It's a little I with a little hat on it. So we call it I hat, okay? The j is the unit vector along the y-axis. It's called little j hat, not little j hat, j hat, okay? So we have I hat and j hat. Turns out that in 3 dimensions when we have a z-axis, we also have k hat, but we're not going to talk about that right now. Okay. Now, considering the vectors below, you've seen these 3 vectors. We talked about these vectors when I introduced to you the idea of quantifying the angles of vectors. Okay. Now, what I can do is I can make this table, which I alluded to last time. I can break each vector into its x and y components. And the rule of adding vectors that I discussed last time was that the x component of the resultant vector is the addition of the x components of a, b, and c, and the y component of r is the sum of a, y, b, y, and c, y. And I can write it like this, okay? Now, calculating each of these, you can check my math. I end up with rx equals 24 and ry equals positive 11, which means that this resultant vector for all these vectors points is in the first quadrant, right? Because x is positive and y is positive, okay? Now, another way of writing these vectors is like this. I could, instead of writing x component, y component, and all that business, a really nice way of writing it would be a equals 38.8 I hat plus 20.1 j hat. This tells you immediately that this is the x component because you have the I hat, and this is the y component because you got the j hat. Look at my other numbers. I'm just taking these numbers and I'm translating them into I hat and j hat speak. So that's why we use unit vectors. It's a very nice and neat way of quantifying vectors, and I will use them in class quite a bit. So I expect you to know what I'm talking about. Okay? All right. Another couple of things which you will study in your math class. I will introduce to you now. It makes sense. These are not in the IB syllabus for physics, but they're very, very useful. This is the dot product and the cross product, and they're really cool. These are ways that we multiply vectors, okay? All right, so the first one is called the dot product, and what it does is it actually multiplies parallel components of 2 vectors together. And we'll work through some examples visually in class. I won't do it in this video, okay? And the way that we do the dot product is we actually do A, B, and we actually make a dot in between. That's why it's called the dot product. And it's understood to be the magnitude of A times the magnitude of B times the magnitude of the cosine of theta, where theta is the angle between A and B, okay? All right, we just say A dot B. It's cool. The result of a dot product obviously is a scalar because I'm multiplying 3 scalar values together. Okay. So, for example, some examples in physics. We're going to study this later. Work done is the product of force times distance, but it's really the dot product of force and distance because we only consider the components of the force and I said distance. I meant displacement. We only consider the components of force and displacement that are parallel to one another. Another example, magnetic flux, which is A dot B. Okay. Now, the cross product multiplies the perpendicular components of 2 vectors together, and it's given by A cross B. We say A cross B, and it's a big cross. It's not like an X. It's like a big cross, right? A cross B. okay, where so it's AB times sine theta, where A is the angle between vectors A and B, okay? Turns out that the result of a cross product is a vector that is perpendicular to the two vectors being multiplied, okay? And that's because the sine of theta gives us only the perpendicular components of two vectors when they're multiplied together. And we say it's A cross B. Some examples in physics that we use, the magnetic force on a moving charge in a magnetic field is F equals Q times velocity cross V cross B, right? So that's QVB sine theta. We'll study that next year in my class, okay? Now, you need to be able to think and work in 3 dimensions in IB physics, okay? In 3 dimensions, I talked about this a little bit last year in physics. If you had me, you remember the x-axis, the y-axis, and the z-axis? Well, you can visualize them kind of like this, okay? Now, in a 3D coordinate system, you consider 3 different variables for each point in space. Before, in a 2-dimensional system, you had x comma y. Now you have x comma z, so you have three numbers that you need to consider. They're always in the order x, y, z, okay? Just like 3 comma 2 was always understood to be the x coordinate was 3 and y would be 2. It's always in order x, y. It's always in order x, y, z. 2 axes are in the plane of the page, and the other is out of the page. So you can see in this case, the z-axis is coming out towards you. The positive z-axis is I labeled it here, and the negative z-axis is going into the board or into the page or into the computer or whatever it is you're viewing this on. Okay, all the axes are orthogonal, meaning they're all at right angles to one another. In this case, now there are 3 unit vectors here: I hat, j hat, and k hat. Okay, the k hat refers to the z-axis. All right. Now, in this case, R is now the sum of 3 component vectors, Rx, Ry, and Rz. When a vector goes into the page, we represent it by an X, and when it comes out of the page, we show it with a dot. And the dot, you can imagine, is the tip of a head of a vector coming out right towards you. Okay? So, again, out of the page, into the page. Okay? All right, here's a little example for you. Okay? All right, I want to plot the point 2, 3, 2 on the following 3D coordinate system. All right, well, 2 corresponds to x, 3 corresponds to y, 2 corresponds to z. All right, go ahead and try it. Maybe you just try tracing it out with your finger if you want. I don't think you have this diagram. See if you can figure out where it's going to be. Well, the first thing you want to do is you want to go positive 2 on the x-axis, which is shown by the dashed red arrow here. Okay. Then you would go positive 3 on the y-axis, which is upwards, okay, right here. Now, notice that this point in space where my red dot is in the 2-dimensional plane, which is the same as the plane of the paper or the computer, okay? Z will bring it out towards you because my z coordinate is positive. So it's going to come out like this, and it's going to be exactly 2 long. So this point right here is a point hanging out in space, which is actually hovering above the plane of this paper or the computer screen. Okay. Now you can think of it if you put a little box, like a little 3D box around it. Okay. This point in question, the point that we're interested in, given by 2, 3, 2, is the corner of this box where the other opposite corner is actually at the origin. Can you see that? Okay. It's really useful to sketch that box if you, in order to view it, right, in 3-dimensional system. When working in 3D, use the right-hand rule, where the 3 dimensions are represented by your thumb, index finger, and your middle finger, kind of like that. We will use the right-hand rule all the time when we study, when we study lots of things towards the end of the first year, electricity and magnetism, and all kinds of cool things. All right? Okay. Now, this last section of this video, I'm going to basically do some examples for you and show you a 6-step process for resolving vectors and finding resultant vectors analytically. It's a procedure that keeps things simple and logical. You should follow it every single time. The reality is that when you get good working with vectors, you might not follow it exactly. You're not required to follow it on the IB exam, but it's a great way of keeping track of things. So I'll show it to you, okay? All right, the first thing that you want to do, and again, this is a process for finding resultant vectors by components, breaking vectors into components. And remember, every vector in the universe can be broken into components. So this is pretty universal. All right. First thing you want to do, draw a diagram carefully using a straight edge and a protractor if appropriate on graph paper if possible. You want the diagram to be as accurate as possible, but don't go crazy beating yourself in the head, making sure that everything is perfectly the right length and the right angle. Just be reasonable. Okay. Step 2, find the x and y components of each vector using trigonometric functions as appropriate. We've done that. Step 3, here's your table. Make your table to keep track of your x and y components of all vectors. Make sure you include positive and negative signs in your magnitudes of the vectors right here. Okay, so just make a table every single time. Make things easy for yourself. Okay. Step 4, use Pythagoras to determine the magnitude of r. Now that you have rx and ry, we've done that before. These are things we've already done doing examples in this video. Find the angle of r. Usually the inverse tangent function is easiest since you've already found rx and ry. Okay? And then you want to refer back to your diagram to make sure that your final numbers make sense. Pay particular attention to the signs of rx and ry and what quadrant r is in. This is why it's good to have that diagram. If your resultant vector analytically is not in the right quadrant or approximately the right angle, you'll know right away. Be smart when you're solving problems. Okay? All right, here's an example. Go ahead and pause the video and try this one using the 6-step method that I just outlined before. Okay, so a couple of vectors here. We have A and B. Find the components of the vectors. All right. The magnitude of A is 10 units and the magnitude of B is 20 units. And you can see that A is 45 degrees below the negative x-axis and B is 30 degrees below the positive x-axis. Okay, so I've redrawn this. Here's my AX, my AY. Bx, by, 20, I've labeled the magnitude, so we're good here. Okay, all right. Okay, so note that the sine of 45 equals ay over 10. Okay, that's correct. All right, so you really want to look at this. Notice that I'm saving myself a step here because I'm noticing that this is a 45, 45, 90 triangle over here, so ax and ay are the same magnitude, but not the same vector. So they're the same length, okay? All right? Okay, whoops. And actually, I guess I didn't use the 6-step problem-solving method because I actually was not being asked to find the resultant vector of these two vectors, was I? So basically, this is just asking find the components. These are the components. And since I don't know what the units are, I just put units. So always put units even if you don't have units. Yeah. Okay, example 4. All right, pause the video and check out this one. Okay, I'm given two vectors. Find the magnitude of A and B and A plus B. You're crazy if you don't draw them. Draw them on graph paper. Okay, I have here 4 squares equals 1 unit, which is somewhat irrelevant to you because you can't even really see the squares. All right, but anyway, let's see. So what did I do here? Okay, magnitude of A and B. And of A, B, okay. Okay, good. So now I'm adding A plus B, all right? Now, the magnitude of A and B, that's very interesting, okay? Yeah, we have some symmetry here, right? Okay, so A equals B, the magnitude of which is root 2, okay? And to do A plus B, here's my finding a resultant vector. So here's my table, okay? X components, Y components. Notice that A plus B has no Y component. Visually, it's because, yes, it points along the x-axis, okay? So I have A plus B is 2 comma 0, or 2I hat. I wouldn't even have to say 0j hat. And the magnitude of A plus B is, in fact, 2 by the Pythagorean theorem. Okay. All right. Example 5. Pause the video. Try this one. Draw these vectors on this piece of graph paper. Pause it and draw the vectors. Trust me, you want to do that. Okay. So I have A and B. I want to find a vector C such that A plus B plus C equals 0. Well, this seems like a hard problem. This probably you should have spent some time working this problem before you look at my solution. Here's your last chance. You can pause the video up. Okay. Well, I assume that you did it. All right. Now, note graphically that C equals negative 3I hat, negative 3I hat, negative 1j hat. So graphically, this is what's going on here. A13, B22. Yep. Okay. All right. Okay. So analytically, here we go. A plus B plus 3 plus 1. Okay. And this is what I got. Now, let's see. Yeah, so the other thing, I didn't really highlight this. When you see a vector written like this is somewhat unusual. This is 2 is the x component, -2 is the y component. 1 is the x component, 3 is the x component, 3 is the y component, okay? So this is just basically like saying A equals 1i hat plus 3j hat. B equals 2i hat minus 2j hat, and so forth, okay? So you really want to, I don't know how you solve this problem, but you really want to look at my solution, especially my answers, and make sure that what you got is in line with what I got. I suspect you might want me to go over this one in class. I'm happy to spend as much time on it as you need.